Yes, Assalamu alaikum again. So, as I was discussing that today we gonna discuss about another type of spectroscopy, which is being called as IR spectroscopy, or it is being referred to as infrared spectroscopy. You will see that most of the stuff would be same because the principle would remain the same. Only the difference will be in terms of electromagnetic radiations. We all know that the electromagnetic spectrum ranges from infrared to visible, and from visible to the other regions of the electromagnetic radiations. So the basic would remain pretty much same, but there will be a couple of things that we're going to add on today when we discuss about this another type of spectroscopy. Let me see, this is the wrong presentation shared with you guys. Just hold on. So, yep, that's the one. So we're going to start today with the infrared spectroscopy. The basic principle, as I was saying, would remain pretty much same, that how the working of the technique takes place and how the interpretations are being done. But there are some technical aspects that we want to add on to this infrared spectroscopy. Let's start with this. I'm just quickly going through these couple of slides very quickly because that's part of the intro, which you have already started. That spectroscopy is a technique of analytical biochemistry, which is primarily used for both qualitative and quantitative determination. So this is basically a technique where a particular wavelength of an electromagnetic radiation will pass through a sample. And as a result of the interaction of that electromagnetic radiation with that sample, we either determine the absorbance of that particular light by the sample, or we determine the transmittance, the light that passed through the sample. So either way, by measuring the amount of light absorbed or the amount of light transmitted, we can find out specific information about that sample, about that compound, or about that specific functional group a compound may have. So in IR spectroscopy, as the name itself is self-explanatory, that is infrared. Infrared is a particular region of the electromagnetic radiation spectrum, which is having a particular wavelength. So IR spectroscopy is primarily concerned with the study of absorption of the light. Which light? The infrared radiation light. And as a result of the absorption of that IR radiation, that results in a change in the molecule that absorbs the light. And that change would be either vibrational or it could be transitional change. Now, what actually happens that when a specific light of specific wavelength, which is infrared, is passed through that sample, the sample will absorb the light, and as a result of that absorption, there is a vibrational change in the bonds within the molecule, and that particular measurement is referred to as vibrational spectroscopy. Now, in IR spectroscopy, we mainly use this technique to identify specific functional groups within the molecule, but it's not limited to that. It can also give some information about the number of bonds present in a compound, the specific type of isomers like stereoisomers, and the arrangement of the atoms in the molecule. So we can say that this IR spectroscopy is a bit of more specific type of the spectroscopy, where we are not only interested in looking at the concentration of the molecule, which we used to do in 411 and 412, where we have the visible spectroscopy, and the primary objective was the measurement of the concentration of a particular compound. But here, it's more towards identification of a specific functional group in a molecule, information about its isomeric structure, information about its number of bonds, and atomic arrangement of that particular molecule. So that's mainly the objective of this IR spectroscopy. Now, in terms of the electromagnetic radiation spectrum, this picture is being shown here again. It's not actually the complete one, but it's just being focused on infrared, and you can see this the middle portion between light yellow to dark red or blackish. This particular region, which is being shown here, that's the infrared region, and we are technically at this stage interested in knowing about this. But this is the whole electromagnetic spectrum where you can have the cosmic rays and ultraviolet, which we have already studied, and then that particular portion of the visible that we have already studied, and then beyond infrared we have microwaves and radio waves. So what we are interested in this infrared region. So in IR spectroscopy, we are concerned with the absorption of only infrared radiation. And as I earlier said, that when the infrared radiations are absorbed, it results in the vibrational transition of the bonds within the molecule. So that's why this type of spectroscopy is also being referred to as vibrational spectroscopy. Now, in this diagram, the thing that I want to make sure to explain is that this infrared region is somewhere from 3 micrometer to 30 micrometer, which is called MWIR. That's the main region of the infrared radiation. While we have a region which is beyond 30 micrometer, which is called FIR, which is far infrared region, and there's a region below 3 micrometer, which is called NIR. So we have two regions which are on the either side of the spectrum of infrared, which is far side and the near side. We are not pretty much interested in this NIR and FIR. The portion which is going to be absorbed specifically in infrared spectroscopy is that MWIR region, which is lying in between 3 micrometer to 30 micrometer. So this is the specific part of the infrared, spectrum, which is going to be considered in the infrared spectroscopy, and that's the particular part of the radiation which is being absorbed. And as I said, as a result of that absorption, there is a change in the vibrational transition of the bonds of that molecule, and that's how we determine the information which I mentioned earlier, like what type of functional group are there, how many bonds are there, different types of the isomers, and etc. So the same picture is being explained a little bit in more detail here. And as you can see that this was the portion I was actually talking about, which is called the mid-IR region, which was shown in the previous picture as well. So you can see that this mid-IR portion is somewhere lying between 2.5 to 5 micrometer, or in terms of the wave number between 4,000 to 200 cm. While we have two regions on the either side of the mid-IR, which is called the near IR, NIR, and far IR, which is FIR, that has been shown in the previous picture. Now, I'm not very interested in these specifications of the wavelength. The only thing that I want to make emphasis on is that this mid IR is actually the one which I mentioned is appropriate for all IR spectroscopy analysis. The reason, because it gives a fully IR peak in IR spectrum. When we do the IR spectroscopies, as we said that the light is being absorbed. When it is being fully absorbed, it gives the vibrational change, and as a result of that, there is a spectrum which is being given to us, which leads to the determination of the characteristics which I mentioned earlier. So in case of the near IR and far IR, they are either so close to UV or they are so close to the radio wave on either side, and that's why they sometimes interact and form extra unwanted spectra, which may interfere with our own, very much interested molecule of interest. So this is the point to be kept in mind, that when we do the IR spectroscopy, the amount or the region of the IR we are primarily interested in this particular type is the mid IR region, which, as I said, is appropriate for IR spectroscopy, and it gives a fully IR peak on the IR spectrum, and the range is between 2.5 to 5 micrometer. Now, when it comes to the principle of IR spectroscopy, as I said earlier, that the main principle would remain the same. Like if you talk about the overall consideration of the spectroscopy, we know that the main principle would remain the same, but there will be a slight difference when you are going to discuss about visible spectroscopy, ultraviolet spectroscopy, and IR spectroscopy. So, what specifically in this case, when IR radiation, we pass on this IR radiation through the sample. These IR radiation, they interact with the sample molecule. As a result of that interaction, as I said earlier, the sample molecule will absorb the specific applied quantized amount of the IR light. Now, why we say that is specific? Because now, depending upon the structure, depending upon the atomic arrangement, depending upon the number of the bonds, depending upon the functional group, the molecule, the sample will have different tendencies to absorb light. And that's how it gives you the idea that with the help of this technique, you can identify them. So when the IR, they are being passed through the sample molecule, it will absorb the applied quantized IR light, which is then matched with the internal vibrational frequency of the molecule. So when the molecule will absorb that IR light, it will matches with the internal vibrational frequency of that particular sample. And of course, there are some residual frequencies which will not be absorbed and they will pass from the sample. Just like the basic principle I was talking about spectroscopy is, when a light is being passed through a sample, some amount of it is absorbed and the rest of it is transmitted. So the same principle applies here. A specific IR light will be absorbed based on the matching with the internal vibrational frequency of that sample, and the rest which is not absorbed will be transmitted through the sample. Now, as a result of this, the absorption of IR radiation, there will be a net change of the dipole moment in that particular molecule. I'm sure that you guys will be aware of what is dipole moment. When there are two poles, negative and positive, within the molecule, they would have a specific attraction between those poles, and that is being called as dipole moment. So the molecules, they do have dipole moment because of the change of the electronegativities, and as a result of that absorption of the IR, the molecule's dipole moment is changed. And as a result of this, there is a change in the vibration of the bonds, as I said earlier. And as a result of the change of the vibration of the bonds, the molecule will either undergo stretch, that means it is a little bit stretched, or it will undergo some sort of bending. So that means the vibration itself could be of two types. And one type is stretching, and the other type is called bending. So let me summarize again. When a specific infrared radiation is passed through the sample will absorb a specific amount of that IR quantized light depending upon its own internal vibrational frequency. The remaining of that will transmit out. As a result of the absorption of the IR, there is a change in the dipole moment of the molecule that in turns result in the vibration of the bonds. And as a result of the vibration of the bond, they might undergo stretching, or they might undergo bending. Now, what is stretching and bending? I'll explain this later on. So the transmitted light, on the other hand, is detected by the detector, because once the light passes through the sample, that is called the transmitted light. And on the other side of that, there is a detector which is specifically being there to detect that light. So the transmitted light is detected by the detector, and IR spectrum is made. And this IR spectrum is interpreted on a computer screen the by the analysis of the transmitted light. This is a pretty much automated technique. It's not like what you guys were doing in 411 and 4212, where you found the OD and you draw the graph. These instruments are pretty much sophisticated and they are automated. So you can see the picture here. This is the IR spectroscopy, which is connected with a computer through a software. So it's all automated. You put the sample there, you select the wavelength, you start the process, the light is passed through the sample, some of them is absorbed while the rest of that is transmitted. After the transmittance, it is going to hit the detector, and the detector is going to transform that into signals, which are being shown as a graph on the computer, as you can see this one. So this is a typical graph of percentage of the transmittance versus the wave number. And this particular graph is the tool by which you're going to determine the structure of the molecule, the nature of the molecule, the isomer of the molecule, the number of the bonds, and so on and so forth. This is another diagram, just to give you the process, illustration. You can see that this is more of a detailed, I would say, elaboration of how the functioning of the IR spectroscopy takes place. This figure is of the Fourier transform spectrophotometer, and what actually is happening in this, we have a source energy. Definitely, whenever we are using either UV spectroscopy, visible spectroscopy, or IR spectroscopy, there should be a source of light. And so in this case, we have a source light or a source energy, which is first going to strike a beam splitter. Now, the function of the beam splitter, you can see here, this one, is just like a device that is split the beam on the basis of their wavelength. So when the energy strikes the beam splitter, as the name itself is indicating, that beam splitter is going to split the radiation or the wave and produces two beams of roughly the same intensity. One beam is going to strike the fixed mirror, which is being shown here. You can see. And the other one is going to strike, the first one is going to strike the fixed mirror and then coming back to the beam splitter. The other beam goes to the moving mirror, which is being here. So this is stationary and this is moving. You can see the split takes place. One beam goes here, one beam goes here. And after that, these two beams then come back and meet up again at the beam splitter. So what beam splitter has done? It splits the wave into two of almost same intensity. One goes to the stationary and one goes to the moving mirror. After striking with them, they come back and they reunite, you can see here, again at the beam splitter. So when these two beams meet up again at the beam splitter, they recombine, and that recombined beam will then passes through the sample. After that sample, you can see few of the amount of the light is absorbed, as we all know. The rest is being transmitted, strikes the detector, and then detector will transform that from with the help of the software on the computer, and then you got this particular spectrum. So this is one type of IR spectroscopy, which is called Fourier transform spectrophotometer. So as I said, that as a result of the light, specific IR quantized light absorbed, there is a change in the vibration, as I said earlier. And I mentioned to you that vibration could be of two types, stretching and bending. Now here comes the detail. What is stretching vibration and what is bending vibration? So The point is that when the IR quantized light is absorbed, it results in the vibrational change of the sample. And that vibrational change can either be a stretching vibration or it can either be a bending vibration. The stretching vibration is always of higher frequency, while the bending vibration is always of lower frequency. And I think you can guess from the term itself. Stretch means the bonds become more stretchy, they move away. That's why it's higher frequency. While in the bending vibration, the bonds will come closer, and as a result of that, it has lower frequency. Now, this stretching vibration can further be classified into two types as symmetric and asymmetric. And the terms are again self explanatory. You guys know what is symmetric and asymmetric. The pictures are being shown here. You can see that in this case, the stretching is, symmetric. Both are in the same direction. While here, the stretching is asymmetric because the directions are different from one another. In case of the bending vibration, they are also of two types. One is called in plane bending, and the other one is called out of plane bending. Now, again, let me revive this concept of plane. You know that whenever there's a molecule, there is a line in between dissecting, which is called the plane. And the molecules which are above the plane and molecules that are below the plane. Every geometric shape have got a plane in it. So this bending vibration is of two types. That bending could be in plane or it is out of plane. Now I'll go in further detail with next slide where you go to the symbolic representation to understand what is in plane bending and what is out of plane bending. But let me just quickly go through the in plane bending is further of two types: scissoring bending and rocking bending. While out of plane bending are of two types: twisting and wagging bending. So it is to note down that the number of bending vibration is usually more than the number of stretching vibration, as you can see from this flow chart. So here comes the diagram which gives you more better understanding of what actually I was talking about: stretching vibration, and then it's two types, and then bending vibration, and it's four types. So for the stretching vibration, I already have explained to you that is symmetric and asymmetric, and you can see they are in the same direction, symmetry, and that is asymmetric vibration. While in order to explain, we know that in symmetric stretching, the bond length increase and decrease symmetrically. That's why it's called symmetric stretching. While in the asymmetric stretching, there should be the length of one bond increase more than as compared to the decrease of the other one. So that's how it's called the asymmetric stretching. In case of the bending vibration, as I said, there are four types of the bending vibration, and that involves the change of the angle. While in stretching vibration, there is no change in angle, it's just the stretch. While in bending vibration, there is change of angle. That's why we call it bending vibration. So the four types are scissoring, rocking, wagging, and twisting. We'll go through them one by one and with the pictures as well. Scissoring is the movement of two atoms towards and away from each other. So scissoring is the movement of the atoms or the bending of the atoms towards and away from each other. So the bond angle decrease and increase with time. Now this is scissoring, you can see. So these are the movement of the two atoms towards and away from each other. This is particularly called as scissoring. While in the rocking model, the bond angle is maintained, but bond moves within the same plane. That means changing the angle between the group of atoms. This is called rocking model, right? You can differentiate between the scissoring and the rocking model. While in case of the wagging, in which both atoms move to one side of the plane, and in this case, changing the angle between the plane, a group of atoms. So in wagging, both atoms move to one side of the plane. You can see this one. Both atoms are on the charges are on the same side. While in the twisting, one atom is above the plane and the other is below the plane. That's why you can say the charges are there and there. So these are the symbolic diagrammatic illustrations of how I understand that these sort of bending, they are very difficult to understand when it comes to a 2D picture, because this is actually a 3D structure, which is very much difficult to understand by the 2D. But I'm sure that these pictures will give you a bit of understanding that what actually rocking, scissoring, wagging, and twisting, bending vibrations are. Okay, let's go further. What are the conditions or criteria to absorb IR? As we earlier said, that different molecules would have different capacity to absorb IR, and definitely different capacity to transmit, because what is absorbed, but the residual amount is going to be transmitted out. So there are a couple of conditions or couple of criteria that could be used in this case, which might be, um, for example, when applied infrared frequency is equal to the natural frequency of the vibration. Remember, the sample, the molecule, do have its own natural frequency of vibration, because all the particles are in vibration. We all know the atomic concept of vibration of atoms. So when the applied IR frequency is equal to the natural frequency of the vibration of the molecule, then the absorption takes place and a peak is observed. It's all about syncing. When there is a synchronization between the applied frequency of infrared and the frequency of the vibration of the molecule itself, then there's a peak. That means more of the light is absorbed. Only the molecule gives IR absorption, because the molecule itself is not being able to absorb UV or visible light. The molecules must have a dipole moment, I mentioned earlier on, because as a result of the IR absorption, the dipole moment is changed. So the molecule which we are interested in determining through IR must have a dipole moment in it. So the non-polar molecules cannot be figured out or determined by using this technique. The mode of vibration of the molecule should not be center of symmetry. That's why it's either symmetrical or asymmetrical. And the point is repeated, the molecule should be polar. It's the same thing. The point number three and the last one is the same. So it is important to remember that it is not necessary for a compound to have a permanent dipole moment to be IR active. Now, this is another very important point. Like, there are certain compounds which are polar, but under the normal condition, they don't have dipole moment. The reason could be they are symmetric. But as a result of the absorption of the IR and the bending and stretching of the vibration, that results in the development of the dipole moment. So dipole moment is something which is related to the compound's polarity. If the compound is polar, that can give you a dipole moment. But in a normal state, if the compound is polar but it's symmetric, you will not see any dipole moment in this. So these are the things to be kept in mind, that the compound must be a polar compound. It might be having a zero dipole moment because of the symmetry, but it may have a dipole moment after, when we throw the IR light on this. Okay, so this is going to be my last slide for today, because I believe that it's a lot of material that we have gone through, and you guys need to go through it again before we complete this topic. So this is going to be my last slide for today's lecture. Now, what are the modes of molecule when it comes to electromagnetic radiation? We know that we have been talking about UV, we've been talking about visible, and we've been talking about IR. It's all about different electromagnetic radiation spectrum. But what is actually mean by the mode? Mode means whenever the electromagnetic radiation passes through the sample, what sort of changes we observe. So modes could be of three types: translation, rotational, and vibrational. To explain this, we should know about the degree of the freedom. What actually the degree of freedom is? Now, we calculate the degree of freedom as the total number of the degree of freedom can be found by having the translation change plus the rotational change plus the vibrational change. Multiply by the degree of the freedom. Or in other case, if we take out the vibrational degree of freedom, that will be the multiplication of these three, 3n, and then combination of the translational and rotational energy multiplied by the degree of freedom. Now, what actually I'm interested in this slide, I'm not interested in the mathematical aspect of this. What I want to let you know is whenever the electromagnetic radiations are passed through the sample, it results in three types of changes, three types of modes: translational change, rotational change, and vibrational change. Whatever the change is, it is directly correlated with the degree of the freedom the molecule would have, the degree of the freedom the molecule possess in order to do the translational change or rotational change or vibrational change. So what I'm interested in here is just to let you know that any kind of translational, rotational, or vibrational changes results because of the electromagnetic radiation are related to the degree of the freedom that that molecule would have. So this is the focus of this slide. I'm not interested in the mathematical details of how to calculate that out. So just I quickly explain that if you talk about the total number of degrees of the freedom, it should be the combination of all the modes multiplied by the degree of freedom. And if you are interested in any one of them, like vibrational or rotational or translational, you take it out the vibrational degree, and then it's addition of these two multiplied by the degree of the freedom. That's how you calculate out how the vibrational degree or any other mode can be calculated out. There is an example here just to let you know that, for example, the vibrational degrees of the freedom of CO group, mathematically they are being calculated out. That's 3 into 3 minus 5, which is 4. So I'm not going in the detail that how it's calculated, just to let you know that specifically for the CO group, the vibrational degree of freedom is being calculated, and that comes to be 4. Similarly, for the water, it comes out to be 3. So that shows that every molecule would have a different vibrational degree of freedom that can be calculated out by using these mathematical transformations. So I'm going to stop here, and I'll just open up for the question. If you have any questions, you can ask the question by raising your hand. And meanwhile, I'll definitely upload the presentation and as well as the recording once it is available. So if you have any question, just raise your hand, and then I'll ask you guys to speak up. Thank you very much. So we don't have any question at this stage. Okay, but you can go through the presentation. I understand that it's sometimes very tricky and difficult to get the topic and ask the question. So you can have that presentation. I'll share the presentation shortly on the WhatsApp group, and also the recording of the lecture. You go through that, and if you have got any question, then come back to me. Most probably, the next class would be our last class to finish that 6 to 4 component of spectroscopy. So, inshallah, see you next week. Thank you very much. And inshallah, I'll share the stuff with you guys. Thank you very much. Khuda Hafiz.